Okay, so what we're looking at today are calculations involving the mole and molar mass. So things that we've learned about already, but we're going to kind of put into action. We're going to look at different scenarios that you're going to come across and different things that you can determine by having those values. Okay, so first off, what we're going to look at is if you have the number of moles, but you're asked to solve the number of something. So I said particles here because particles can really refer to anything. So, and I have a note down here to remind us of that. So particles can be how many atoms are there, how many formula units, remember that represents compounds, it's the same thing. How many ions, how many molecules. All of those can be calculated if we know the number of moles. So let's go over some kind of new symbols that we haven't seen yet so far. So capital N refers to the number of what you're trying to solve. So again, I put particles here, but it could be whatever. So number of atoms, number of molecules. Lowercase n represents the number of moles. Capital N with the lowercase a represents Avogadro's number, which we know is 6.02 times 10 to the 23. So the formula we're going to use here is to figure out the number of something, we take the mole value and we multiply it by Avogadro's number. And that should make sense because 1 mole equals Avogadro's number. So let's say I had 2 moles, we would have to do 2 times Avogadro's number, right? This is like, imagine a dozen. If I have 2 dozen, it would be 2 times 12. Same thing. So this is just showing you the procedure. So to get from the number of moles, we can figure out the number of particles, which here are some examples of what we can find. So let's take a look at an example question. So I'll always try to do one and then have you try one, okay? So a small pin contains 0.0178 moles of iron. Okay, so as we go, we're going to kind of jot down what we have. Okay, this is exactly the way I'm going to do these types of questions is how I'm going to expect you to set this up. So number of moles, right, we're using the symbols now that we understand what they are. So moles is 0.0178 of iron. Maybe you want to remind yourself of what that is. What we can also do is put the little symbol of what it is beside the mole symbol. So it says moles of iron. How many atoms of iron are in the pin? So we are trying to find the number of atoms. So I always would like you to, it's kind of like we're doing grasp, right? So as you're going through this, so you're going to have, what are you looking for? The formula is moles times Avogadro's number. And we're going to plug in our value. So 0.0178 moles times. Now remember, anytime you are calculating using a scientific notation number, I'm going to put this in brackets as a reminder for you. But when you put this in your calculator, okay, this calculator the calculator must have brackets when you're doing this. Is equal to, so this is going to be 1.07156 times 10 to the 22 atoms. Okay, now in terms of unit cancellation, I'll show you how this should be. So technically this is atoms per mole. So the moles cancel out. Okay, when you are using Avogadro's number, you do not have to write those. Okay, so like I said, I'm going to show you what I expect for the layout here. So in terms of, you have to understand what it represents, why this becomes atoms, but you do not have to show me. Okay, so at least when it comes to Avogadro's number. So the last thing we need to do, this is our answer, but we have to do this in the proper significant digits. So 0.0178 is 3 significant digits. Remember, leading zeros never count. So this becomes 1.07 times 10 to the 22 atoms. Okay, you do not have to do a paraphrase, right? You normally in GRASP you have a sentence at the end. What I would like you to do, when you're doing these is to put a box or a circle around what your final answer is. Okay, so it's like you're following GRASP, but it's a simplified version of it. Okay, so example 2 has a part B to it. Okay, but for now, what I'd like you to do is try out this first one on your own. It says a sample has 1.25 moles of nitrogen dioxide. How many molecules of nitrogen dioxide are in the sample? Give this a try. All right, let's see how we did. So first of all, we have the number of moles for nitrogen dioxide, which is 1.25 moles. Okay, it's actually a good habit to get into putting this subscript, because as we get further and further into learning about calculations involving moles, you're gonna sometimes have multiple mole values. So it's kind of good to have this and label them what each one is, so you don't forget which one belongs to which compound or molecule, okay? So we have the number of moles, we're looking for the number of molecules. So that's going to be moles times Avogadro's number. I guess I should make that capital. 1.25 moles times 6.02 times 10 to the 23 is equal to. So you should have gotten here. Actually, we'll round to 3 sig figs. So this was 7.52 times 10 to the 23 molecules. All right, so actually we're going to need what the original value was. So the original value, I'm just going to put this up here, the unrounded one, it was 525 times 10 to the 23 molecules. Okay, so the reason why is because for part B. So this is our significant digit answer, right? Part B is how many atoms of oxygen are in the same sample of NO2. So this value here is for NO2 total, like the molecule. So if you remember from our mole lesson, think of this as like a little assembly line. For every one nitrogen, there are 2 oxygens. So for every one NO2, there has to be 2 oxygens to create it. So technically, if I want to know the number of oxygen atoms, I have to take my number of molecules and double it. Because for every one molecule, I need 2 O2, like 2 oxygens to create that molecule. So I'll show you how to set this up. And actually, this is a great point. Any time where you are doing multi-step problems, you do not use your rounded significant digit number to do that next calculation. You always use your original value. So it's actually a good habit. So I should have written down the original one first and then the sig fig, because this is the one we're going to be using going forward. So this is 7.525 times 10 to the 23 molecules. So I'm going to show you how to set this up. For every one molecule, there are 2 oxygens. So the molecule cancels and we get oxygen atoms. So essentially we're just doing this times 2. So for our answer, this is 1.505 times 10 to the 24 oxygen atoms. Okay, now in this question, part B, there is no numbers. Do you see that? So that means you can actually keep this as is. The significant digits is only when you actually have data that has been given to you. So for over here, there's no data, so you're just going with whatever the answer is. It's not expected that you round this. Okay, sometimes students will like to round it anyways because you're kind of in the habit, but you do not, it's not a necessity. Okay, so this kind of part B question is very common. So if I had asked for the number of nitrogen atoms, because it's a 1-to-1 ratio, it actually would be the same number. I would like you to still show your work to prove that. Like 1 nitrogen for every 1 molecule. But it's good to know the understanding of that it would just be the same value. Okay, so the second scenario that we are looking at here. So the second scenario is, what about if we had the opposite? We have the number of particles and we want the number of moles. Well, really all we're doing is we're rearranging that former formula. So before we had N is equal to N times Na. So what we're doing is we're solving for N now. So in order to isolate for N, right, you do the opposite function of what it's with. So because it's times Na, you divide by Na on both sides. So your final formula ends up being N moles is equal to the number over Avogadro's number. So remember, this number can be anything, atoms, particles, whatever it happens to be. And we know that this is 6.02 times 10 to the 23. So let's do an example. So how many moles, so we're looking for the number of moles, of carbon dioxide are in a sample with 5.83 times 10 to the 24 carbon dioxide molecules. So the number for carbon dioxide is 5.83 times 10 to the 24 molecules. Okay, so we know we're going to do N is equal to N over Na. So here we're using 2 scientific notation numbers now. So be sure to put this in brackets in your calculator. Okay, so for this particular question, okay, so let's do this, 5.83 times 10 to the 24. Divided by 6.02 times 10 to the 23. Okay, so we get 9.684385, blah, blah, blah. We know we're going to have to round this, right? So the unit is moles. So for significant digits, right, you always go up to the original question. We have 3 significant digits, so this will end up being 9.68 moles. Okay, so hopefully you're finding this relatively straightforward. Give this one a try. So we have a container, we have a cleaning solution that has this many molecules of ammonia. How many moles are in the container? Okay, so let's take a look. So we have N for NH3 is equal to 8.03 times 10 to the 26 molecules. Okay, we're looking for the number of moles. Moles is equals to N over Na. So we have 8.03 times 10 to the 26 molecules over 6.02 times 10 to the 23. So our answer here is 1333.8870, blah, blah, blah. Because remember, we're going to be rounding this anyways. So we need 3 significant digits. So this is where rounding comes in, right? So I want this to be 3 sig figs. It's more than that. So that means I'm looking here and I'm going to round accordingly. So there's 2 ways you can do this. The easiest way I find is to put this in scientific notation. So if we said 1.33 times 10 to the 123, right? This would be one acceptable answer. And I find that's the easiest one to do. So if you need sig figs, you just move the decimal point and you report however many you need. Or, and we'll do this in the next part,